Okay, I think we'll start. It's now 10 o'clock. Right, okay, so welcome to the enthalpy changes and kinetic lesson for today. See, we only have one person in, so you, sir, may ask questions whenever you want on the chat, and we'll answer it as soon as you do. And with the questions and so on, take however much time you need, and then we'll go over it once you're done. All right, so we can start. So today the video will be recorded. I believe you have handouts at the end of the session, or you've already been given it with questions and the mark scheme. We will be doing some quizzes. I don't think we'll be doing Kahoot Day, but today, but there are interactive polls, and obviously we'll give you all the tips that we can. Right, so roughly the timetable for today will be about 50 minutes to an hour each time. And then we'll take lunch at 12 and have another break before we finish. Today we'll be covering, for the first half, it will be enthalpy, so changes, bond enthalpy, Hess's law. And then for the second half, as you can see, reaction rates, catalysts, and Boltzmann distribution. Again, as I said, if you have any questions, just put it in the chat and we'll answer them. So, enthalpy changes. It's a measure of the heat energy in a chemical system. So the chemical system refers to atoms, molecules, or ions that make up the chemicals. Enthalpy is sometimes thought of as the energy stored within bonds. So for bonds to occur, it requires energy, and that energy is thought of as enthalpy. Now, enthalpy can't be measured in itself, but the enthalpy changes in reactions can be. And so that's what we use to calculate, to calculate changes. So that's a general equation over there, that the change in enthalpy is equal to the enthalpy of products minus the enthalpy of reactants. And it's a very general equation, but we'll go through others that are specific to certain subtopics so that you can use those quicker in an exam. So the enthalpy change, that can be positive or negative, and that's quite important. You'll see throughout the lesson. And this depends on whether the products contain more or less energy than reactants, which means that they're exo or endothermic, which we will cover just now. Now, the conservation of energy, it's basically a law of chemistry, and it states that energy can't be created or destroyed within the whole universe. And so this means that when a chemical reaction is taking place, which obviously involves enthalpy change, heat energy is transferred between the systems and the surroundings. The surroundings aren't always just air. As you'll see, sometimes it can be solutions as well. Enthalpy changes can be determined experimentally by measuring the energy transfer, which again you'll see, between the systems and the surroundings. And energy transfer can either be in two directions, where we get the exothermic or endothermic change. So if energy is transferred from the system to the surroundings, then it's an exothermic change. And as you remember from just before, the surroundings could be air, or it could be the solution in which a chemical takes place. And if energy is transferred from the surroundings to the system, then that's known as an endothermic change. Now, using the conservation of energy, we can say that in an exothermic reaction, the chemical system releases heat energy to the surroundings. So if you just remember when we go back, exothermic means that energy transferred from the system to the surroundings. So when energy is transferred to the surroundings, we can say that it releases heat energy. And this is something that we can measure, which you'll see. So the change in enthalpy, which is also, as you can see, delta H, so that little triangle, this one here, is known as delta. So delta H is negative for exothermic reactions. And that means that the products have less energy than the reactants, which, as I explained, means energy has to be released, which is then a measure of the energy, allowing us to confirm that the reaction is exothermic. And when that energy is released, it's released as heat energy. Now, this is a graph which shows you, it's very important, and it shows you the enthalpy change along the progress of reaction. And so as you can see, the first line up here, that shows reactants, and the bottom one is products. And as I just stated, exothermic means that it releases energy. So delta H is negative. So the enthalpy of the products will be less than the reactants because energy is required to go into the surroundings. And this means that it will obviously be below in the graph, and that means that delta H is negative. And that's just another, this is just another way of showing it. So the chemical system will lose the energy, and so the surroundings gain the energy. And since it's released by heat energy, this can be shown by a temperature increase by a thermometer, which is very useful when doing experiments. Now, the other side of things is endothermic. This means that the chemical system takes in the heat from the surroundings. So energy is transferred from the surroundings to the system. And the flip side of that statement is that delta H is positive. So the products have more energy than reactants, meaning the energy is required to complete the reaction, which is then measured as less energy in the surroundings. And that allows us to confirm that the reaction is endothermic. So using the same principles as before, which we use for exothermic, looking at this graph, we can see that the products have more energy than the reactants. So delta H should be positive. And again, just to reinstate, if the products have a higher enthalpy, this means that more energy is needed. And so they can get that energy from the surroundings. This delta H, or the enthalpy change, not officially, but you can sort of think about it as the surroundings and whether the surroundings are decreasing in heat or increasing in heat. And so if it's decreasing in heat, it means the energy system is taking, it means the chemical system's taking in more energy. So the temperature will decrease. So if you think that the temperature will decrease, or the temperature does decrease, that means it's an endothermic reaction. And if the temperature increases, it's an exothermic reaction. So now that we've just gone through that, we'll do an exam question. Once you finish the exam question, or you think you finished the exam question, just put it in the chat and I'll go through it. So this, as you can see, is the graph that we just showed. So it's part of an energy profile. The graph is called an energy profile, so that's quite important. It will come up in a lot of exam questions relating to enthalpy. And they'll always say it's not intended to be to scale, but that's okay. You don't need to worry about that. Now, this profile shows the reactants, and the axes are labeled, so that's all good. What you need to do to complete the profile are the products, the progress of an uncatalyzed reaction and then a catalyzed reaction, right? And so that will mean that there are two separate lines that you will need to draw. So if we just go back a second, so here, what they require is a line that will go up from the products, from the reactants to the products, obviously a lot smoother than what I've just drawn because that's terrible. And because they have said that you need the progress of both uncatalyzed and catalyzed, that will require two lines to be drawn from the reactants to the products. And it'll also need to label arrows to indicate the activation energies of both uncatalyzed and catalyzed reaction. Now, the graph over here doesn't actually show what you need to do for activation energy, so I'll just go through that now. So if this line relates to the energy, then the axis, so say I've just gone like that. That's just an example, that's not the answer. And you've got products here. This bit here would be the activation energy, okay? And that is labeled as capital E. God, this is hard. And little a. So when they ask you for the activation energies of both uncatalyzed and catalyzed reactions, you'll just need to draw that, label it EA, and also make sure that you specify whether it's your uncatalyzed or catalyzed reaction. If there's not enough space within the graph, a clearer way is just to do some dotted lines, and then you extend that until out of the graph. And then you'll label it EA catalyzed or EA uncatalyzed. So let me just clear that. And yeah, have a go. Let me know when you're done, and then we'll go through the answer. Are we nearly done? Yes, brilliant. So I've been a little bit cheeky here because I know we haven't gone through this thoroughly. Just wanted to see whether how much you know. Obviously, you'll self-mark it yourself. After we do this, we will go through this thoroughly so that you can you get all the information you need. So the answer to this, so they've completed this energy profile. And as you can see, they've got two lines, one for uncatalyzed, which is this line here, and one for catalyzed, which is this line here. And then the uncatalyzed line requires more energy. So the activation energy will be increased. And that's why it's a higher line. And so if they were to draw it on there, this would be activation energy. And you can clearly see that the activation energy of the uncatalyzed reaction is much more than the activation energy required for catalyzed reactions. And that's why it's known that if you do use a catalyst, then the reaction takes place faster because there's less activation energy required, which means that more molecules will reach that level of energy quicker than if it's uncatalyzed. So in terms of the mark scheme, you'll see that the products are at a higher level than the reactants. Then you've got a line going from the reactants to the peak and then back down to the products. And that's what I've just explained here in terms of activation energy. And this peak is, well, it's corresponding to the transition state. So this just means when the reaction's taking place, that's what the transition state is known as. And then the second line with the lower peak is what I've just gone through as the catalyzed reaction. And another mark is for you to label the uncatalyzed and catalyzed reaction correctly. So that's something to keep in mind so that you know you get that mark, is to label everything. And something that a lot of people forget when they're rushing through their exam questions is to put the states. Sometimes in exam questions, they'll mark you down for not putting the states in because it'll be important. And so it's just a good habit to get into to make sure that all of your equations are complete with the states and that you've labeled everything, and make sure that the energy profile axes are labeled as well, because there's a possibility that they'll ask you to do one from scratch. Now then, to go through it thoroughly, we have energy profiles. And as you can see, we've got everything that I've just covered. The activation energy for both exothermic and endothermic reactions, the label, they didn't do this over here, but sometimes you have the label that delta H is negative or delta H is positive, along with a corresponding line, similar to the way that you have to do for activation energy. And again, that's very important to include. It's a good habit to get into. And they use these dotted lines as just sort of an extension so that you can label it clearer. So the one that we had back here, this was for the endothermic reaction. Okay, so remember, endothermic means that the products have more energy than the reactants. And if they have more energy than the reactants, they're taking in energy from the surroundings. And if they're taking in energy from the surroundings, they require more energy for that reaction to take place. And that energy is shown here as this curve. And so the activation energy will be much bigger than the activation energy of an exothermic reaction. Just to go through the exothermic reaction, you've got your reactants and products. Obviously, conversely to the endothermic, your products will have lower energy than the reactants. Now remember, the activation energy is still required to start off this reaction in the transition state. So it's not like the line is just going to go straight down. You've still got that curve of required activation energy, but the delta H, sorry, is always negative. And if they were to ask, as they did in this question here, for an uncatalyzed and catalyzed reaction, in the same concept that was covered here with the catalyzed reaction requiring lower activation energy than the catalyzed reaction. If you apply that same concept, you have your uncatalyzed, say this is uncatalyzed, this one here. This is the uncatalyzed reaction. And so this is that corresponding activation energy. For a catalyzed reaction, as we've just said, the activation energy would be lower. So all you need to do was create a curve. There we go. I'm getting better at that. With a lower activation energy. And then you label that whatever for the catalyzed reaction. So just keep that in mind. And so in writing, I'll just read this out. So in generals, reaction with small activation energies will take place rapidly, as I explained, because more of the molecules or atoms will get to that energy requirement quicker. And so this is because the energy needed to break the bonds is readily available from the surroundings. And therefore, if you go for very large activation energies, the reaction will take place extremely slowly because the energy needed to break these bonds is not so readily available. And so this reaction takes place very slowly, or sometimes not even at all. So that is a possibility. Now, just focusing on activation energy, there are, as you know, atoms and ions are held together by chemical bonds. And during these chemical reactions, the bonds in the reactants are required to be broken by an input of energy. And this is why, so this, if you just keep in your mind, the reactants need to be broken, okay? And the fact that they need to be broken requires energy. It always requires energy for a chemical bond to be broken. And keeping that in mind, when we go back here to the exothermic reaction, that is why the curve goes up primarily before going down. So the curve goes up because the bonds in the reactants need to be broken, and this requires energy. I know I'm going through things over and over again, but it's just to make sure I'm going to drill it in your head. So that when you are doing it in exams, it comes naturally and everything makes sense. So I think it's quite nice to make sure you have a very thorough base knowledge. And from that base knowledge, everything should come easier to understand. Now, after these bonds are broken, new bonds will be required to be made so that they can complete the reaction and form the products. And this energy that is inputted, which is required to break the bonds, acts as the energy barrier to the reaction. Okay, so the energy barrier means that there's a certain level of energy that the bonds in the reactants need to be at to be broken, and that's known as activation energy. As a more concise definition, activation energy is the minimum energy required for a reaction to take place. Okay. Now, for exam technique, I find it quite useful to have checklists for things like this. And so for a checklist for an energy profile, you'll always have energy on the y-axis, progress of reaction on the x-axis. You'll always have your reactant line, your product line. As I mentioned before, you'll have the equation and you'll have the states. You'll have activation energy, which you'll need to label, and possibly a second activation energy if there's a catalyst. And then your enthalpy change line, which will be the arrow, which says delta H is negative or delta H is positive, whether it's going up or down. Now moving on to standard enthalpy changes. Okay, so enthalpy values will vary according to the conditions that the reaction is taking place in. Now, a substance under these specific conditions is said to be in its standard state. So anywhere it says standard state, standard enthalpy changes, and we'll go through a lot more standard subtopics, it means that the pressure is at 100 kilopascals, which is also known as 1 atmosphere, and the temperature is 25 degrees centigrade, which is also 298 Kelvin. Now, I know it's easier to go for 25 degrees centigrade, but try and remember it is 298 Kelvin, because that will just be a better way to think about it. So those are two requirements. A lot of people remember these, and not many people remember this one, which is very, very important. So in any standard conditions, standard states, the solution are always concentration of 1 mole per decimeter cubed. So this says solutions, okay? So liquids, always under standard states are at a concentration of 1 mole per decimeter cubed. Now, to tell if standard conditions are used, we change the symbol for delta H. So this is normal delta H, and then for standard enthalpy changes, you have the normal delta H, then you have this little tram sign, like the London Underground. Now, there are specific standard enthalpy changes of reaction. We'll go through combustion and formation as well. Now, the standard enthalpy change of a reaction, which is also known as delta R H, with your standard symbol over here, is the enthalpy change that accompanies a reaction in the specific molar quantities shown in a chemical equation. Now, I've changed the color of this because there's something that we're going to go through later, which this part of the definition is different, and a lot of people, they don't remember this, okay? So standard enthalpy change of any reaction, okay, it includes the specific molar quantities which are in that chemical equation. So the molar quantities do not need to be changed when you're calculating standard enthalpy change of a reaction. This is obviously understanding conditions with all reactants and products in their standard states. This will be a phrase that you'll see everywhere in exam questions, just because they need to put it there to make sure that you know that these are under standard conditions. And so delta r H symbol always refers to a stated equation, and its value depends on the balancing numbers. And so this is an example of the standard enthalpy change for reaction. So we have magnesium and oxygen forming magnesium oxide. The given molar quantities are 1/2 mole of oxygen, 1 mole of magnesium oxide, and this obviously balances out. And so the standard enthalpy change of this reaction is -602 kilojoules per mole. If it's -602 kilojoules, if you just put it in the chat, is this an exothermic or endothermic reaction? Just write it in the chat. Exothermic. So if you remember an exothermic reaction, I'll go back to the slide, or actually I'll just go through it. For an exothermic reaction, the products have less energy than the reactants, and this means that the energy has to be released, and that means delta H is negative. So well done. You don't need to put question marks, you just got to be confident, go for it. What's this? Right. If the equation is balanced with whole numbers, which we'll look at now, the amounts are doubled and the enthalpy change is doubled because there's double the reactants, okay? And so this is the same equation, just with the moles doubled, sorry. And so we've got 2 Mg plus O2 goes to 2 magnesium oxide. This means that delta H is now minus 102, 1204. And if you remember, that is just doubled the equation which we had here. So if you just look at the equation, you've got 1 mole of magnesium, half a mole of oxygen, 1 mole of magnesium oxide. And here we just have it doubled. And this means that delta RH under standard conditions is doubled the enthalpy change. Now we're going to go through some exam questions. So the first one would be define the enthalpy change of, actually we'll go through it first. That would probably be smarter, wouldn't it? Right, so there we go. The standard enthalpy change of formation is the enthalpy change that takes place when 1 mole of a compound is formed from its elements. This is what I was talking about. So when it's formation, okay, it's 1 mole of a product compound which is formed from its elements under standard conditions with your reactants and products in their standard states. And so with compounds, this is usually a fractional equation for magnesium and oxygen. And this gives the enthalpy change for formation of 1 mole of a compound. And so as you can see, sorry, this is the same reaction that we had before, okay? But this is specifically for 1 compound, 1 mole of this compound, okay? And so the enthalpy change will be the same, but so the standard enthalpy change of formation is the same throughout, okay? So just remember that. This is for 1 mole specifically. And so with compounds, if we just go through this definition, this will be the enthalpy change for the formation of 1 mole of this compound. And with elements, I'll just read it out. From its definition, the enthalpy change of elements for an element refers to the formation of 1 mole of an element from its element, okay? This means that there's no change, right? So all elements have an enthalpy change of formation of 0 kilojoules per mole because no bonds are being broken, no bonds are being remade. Now we will go through this exam question. First one is define the term enthalpy change of formation. Second one is in delta HF, the little f is the elements, formation of elements or a reaction. What are the coordinates indicated by that little symbol on top, which I believe is theta? Let me just double check that because I do not want you to have the wrong thing. Yes, it is theta. So if you want the proper name, that's theta. But in chemistry, just remember it as standard states. And then the third one is write the equation, always including state symbols that represent the standard enthalpy change of formation for carbon monoxide. So if you could go through that and then let me know in the chat when you've finished. So just put it in the chat once you're done. Right, we'll go through the answers. So the enthalpy change of formation is when 1 mole of substance is formed from its elements. Okay, so for an exam question of like this, you've got 1 mole of substance, excuse me, which is 1 mark, and you need to state that it's from its elements. Okay, that's the specific thing about formation. You always start with its elements, and then you will end up with 1 mole of the substance product. Now, in delta HF, with the little theta sign, which is representative of enthalpy change of formation, what are the conditions indicated by the symbol? Now, if you remember, we said that theta means standard states, okay? And standard state is 1 atmosphere or 101 kilopascals, and the temperature is 25 degrees centigrade or 298 Kelvin. And that would be 1 mark. So if you miss one of these, then you will get no marks. So make sure you have both of them. I think that's quite important, okay? So that's a very easy mark for you to get in an exam. And so remember all the time, it's 101 kilopascals and the temperature is 25 degrees centigrade or 298 Kelvin. Now, the third one is an application of this knowledge. Write the equation, including the state symbols that represent the standard enthalpy change of formation for carbon monoxide. And they've given you CO. And now this would be carbon plus oxygen, go to carbon monoxide. They've put the states in and they've made sure that they've changed the molar quantities of the reactants so that 1 mole of carbon monoxide is formed. Okay, and that would be 2 marks. And that's what we've just been through. Now we're going to do some more application. You've got my question, I think. Can you round it to 100 kPa? Absolutely not. No. You need to be very specific. It's 101 kilopascals and then 298. 298. Just make sure I've got that right. I am dyslexic. 298 Kelvin. So no, always remember it's 101 kilopascals to be very specific. Now we're going to do some more application of standard enthalpy of formation for the following compounds. So you've got NH3, CH4, and H2O. Okay, and so go through them, and then when you're done, write it in the chat, and we'll go through the answers. And try and remember everything that you need to include to get all of the marks for this standard enthalpy of formation. So let me know once you're done. Cool. So we'll go through the answers now. So for NH3, we've formed 1 mole of NH3. And so this means in a balanced molecular equation from its elements, you've got half of N2, which is the standard of its element in the gaseous form, plus 1.5 H2, again in its gaseous form. And this forms that 1 mole of NH3. Now, you can write 1.5 as 3/2. Okay, that will be completely fine as well. And CH4, that's the same thing. So we've got carbon, solid form, 2 hydrogen compounds as its element, and this forms the 1 CH4 in its gaseous elemental molecular state. And for H2O, you've got H2 plus half of oxygen goes to H2O. So just put on the chat if that was okay. It's quite important to make sure you get these right. Is that all right? Or do you have any questions? How does hydrogen have 1.5? Right. So because we have NH3, oh, yeah, there we go. You can see that we have 3 hydrogen atoms. Okay. And for 3 hydrogen atoms, each side of the equation needs to be balanced. Right. So because, as you can see, there's 1, excuse me, there's 1 nitrogen atom and 3 hydrogen atoms. It needs to be balanced for the 1 mole of NH3. And so if you have 3 here and we have 2 here, using maths to get from 2 to 3, it's required for you to have 1.5. Okay, and that's just a balancing of the equations on each side. All right, does that make sense? Yes, brilliant. All right, it's now 48 by my clock. So we're going to take a 12-minute break. You can come back at 11. And then we'll go through standard enthalpy change of combustion and standard enthalpy change of neutralization, and then move on to actually measuring these enthalpy changes in an experiment. So if you have any questions, I'll be on here for about a minute, and then we'll take our 10-minute break. If you don't have any questions, just put it in the chat and we can take the break. Cool. All right. So I'll see you in about 10 minutes and we'll go through combustion and neutralization. Thank you. All right, it's just past 11. Are you back? Just put a little yes in the chat and then I'll carry on. Yes, all right, brilliant. All right. So next we'll go over the standard enthalpy change of combustion. This is defined as the enthalpy change that takes place when 1 mole of a substance completely reacts with oxygen under standard conditions with your reactants and products in a standard state. So with the one before formation, which we just did, it was 1 mole of the product. So that was on the right of the equation. And this is 1 mole of a substance, which will always be on the left of an equation that completely reacts with oxygen, which is combustion. So when a substance reacts completely with oxygen, the products are the oxides of its elements in the substance. And so we'll just go through the equation for the combustion of 1 mole of butane, which is C4H10. Now, C4H10, we have 1 mole of that, okay? And then we have 6.5 O2, which goes to the products, which are 4 CO2 or carbon dioxide and water. Now, I know earlier you asked me about the 1.5, I believe it was 1.5 hydrogens. So I'll just go over why we have 6.5 oxygens. It's the same principle that we need to balance this equation, okay? Because the definition and one of the most important thing is that we have 1 mole of C4H10 of butane, okay? So one of the ways that you could do this, right, is you've got C4H10, all right? And bear in mind, this is just working out, okay? This is not the answer. This is just a technique that you could use to help you work out how to get to this answer, okay? So you have your C4H10, which I'm just going to put here. And then you have your plus, you have to bear with me whilst I do this, O2, and it goes to CO2. It will, more often than not, always go to CO2, and water will always be included in the equation. So we have CO2 plus water. Okay, and obviously you have the states as well. Now you have C4H10, which is the only thing that cannot change. 10, right. My bad, that was meant to be H. Just pretend that's the H. Okay. So we'll look at the carbons first, right? So you've got 4 of them that cannot change, right? With enthalpy change of combustion, as the definition says, it's 1 mole of the substance. The substance is butane, so that can't change. It needs to remain as 1 mole. And so if we look at the carbon first, you've got 4 carbons. And so if you look on this side of the equation, okay, you go through each element. You've got carbon here, no carbon here, no carbon here, no carbon here. So the only thing that you can balance with these carbons is this carbon, right? And so for that to be balanced, for you to have 4 carbons on this side, you'll need 4 moles of carbon dioxide, okay? Now, you've got 10 hydrogens, okay? So you've got 10 of them over here, which means that you'll also need 10 hydrogens over here, okay? And so again, that's not hydrogen, that's not hydrogen, excuse me, that's not hydrogen. We've got 2 hydrogen here, H2, and again, oxygen's not carbon, not hydrogen. So this is the only bit of the product equation which we can change, all right? And so for that to happen, for us to get from 2 to 10, 5 moles of water is required. Okay. And so with these two numbers, we've sorted out the moles of butane. All right. So now that's done because we've used the 1 mole. We're not changing that whatsoever. That's completed. Now, what we've got is the oxygen, and we've got the completed the completed moles of the products. Okay, so the next thing we need to do is balance these oxygens, right? So if we count on this side, we've got O2 here, and we've got 4 of them. Okay, so 4 of O2, which is 8. Okay, 8. And then we've got 5 oxygens here. So that's plus 5. Okay, and that equals 13 oxygens in total on the product side. And so for us to balance this out, the same principle which we used before, the left-hand side needs to balance out with the right-hand side. So we've got 13 oxygens here, and this is the only point in the reactant equation which we have oxygen. So this is the only place where we can alter the moles to balance out this side. So here we've got O2, and we are required to find, hold on, no, that won't work. Imagine that's a box, not an oxygen. And we need that to balance out to 13, okay? And just to rearrange that equation, that means that our box, yes, is 13 over 2, which is equal to 6.5. And so that is what you will write over here. And then the complete equation is balanced. If you write 13 over 2, that's also fine. You don't need to change it to 6.5. This is very hard to use. Well, you know it's 6.5. Okay. Do you have any questions about that? No. Brilliant. All right. So the equation could have been balanced without fractions, but it would not match the definition, which requires 1 mole, the combustion of 1 mole of CH4. Okay. And combustion always takes place with oxygen. Now we're going to go through the equation for Standard enthalpy of combustion for these compounds. And I'll just reiterate that you need to balance these equations with the left-hand side and the right-hand side in terms of the elements. So take your time with this. If you want to use my method, feel free, but take your time because these can be quite tricky to do at first, but once you get the hang of it, it's much easier. So yeah, off you go. Let me know when you're done, and then we'll go through the answers. Oh, and just to note, the products will always be CO2 and H2O. So you can use that. So that will always be on the right-hand side. So you can use that to balance the equation with oxygen as well as the combustion. All right, let me know when you're done. Are you nearly done? Because we'll go through the answers too. Yes, done. Brilliant. As soon as you're done, you can just put it in the chat. Okay. So for this one, C2H5OH always reacts with oxygen in combustion, always produces carbon dioxide and water. All right. And so to balance out this equation, we've got 3O2, 2CO2, and 3H2O. And this balances out the 1 mole of C2H5OH. Did you get that one correct? Yes, yes. All right, brilliant. All right, next one, CH4. So the answer is CH4 plus 2O2 goes to CO2 plus 2H2O. Again, same principles, you're balancing the equation. You've got 1 mole of CH4. And so that should be your starting point to balance out the rest of the equation. The last one, C3H8, 5O2 goes to 3CO2 and 4H2O. Just double check, were those all good? Yes, lovely. All right. So now we'll move on to standard enthalpy change of neutralization. And so read out the definition. Standard enthalpy change of neutralization is the energy change that accompanies the reaction of an acid, all right, by a base. So always an acid, always a base, to form 1 mole. There's the important bit, the 1 mole of H2O as the product, one of the products. Understand the conditions with the reactants and products in their standard states. So the main thing here, right, as with combustion, so combustion was 1 mole of the reactants, and this is 1 mole of H2O. H2O will be the product, one of the products, and so that's the bit you need to focus on. And with all of these, you've got specific delta H standard conditions. So neutralization is just neut. And as you saw here, combustion was F. Okay. Right. This is probably the most basic standard enthalpy change of neutralization. You've got H plus, which is acid in aqueous solution. You've got OH minus, again, which is the base in this equation in aqueous solution. And you're producing your 1 mole, just 1 mole of H2O, which is a liquid. And so here you'll get the enthalpy change of neutralization. And now we'll go through the neutralization of hydrochloric acid by sodium hydroxide. So for this one, you've got, so the main thing to focus on here is you've got your H2, okay? H2O, sorry. Your H2O on this side. That's the bit you need to focus on. This is the most important thing when going through enthalpy change of neutralization. So it's given you hydrochloric acid and sodium hydroxide. That's your acid and base. Okay, so for neutralization, you require an acid and a base on the left-hand side of the equation, and then 1 mole of H2O on the right-hand side of the equation. And then you're also going to have another product with most acids and bases. It's only with this simple equation that you just get water. So you've got HCl, hydrochloric acid, and then NaOH, sodium hydroxide, both in aqueous solutions, produces H2O and NaCl, otherwise known as salt. Salt in aqueous solution. Okay. Right. So again, this is the most important part. So you've got 2 hydrogens on this side of the equation because hydrogen's only here, it's not here at all. And so here, if we look at the left-hand side of the equation, you've got 1 hydrogen here and another hydrogen here. So that's 2 hydrogens all together on the left-hand side of the equation, and that will balance out this H2 over here. And now you've got 1 oxygen on this side. And if you look at this, the reactant side, you've also got 1 oxygen. And so that completely balances out the equation. Okay. And so for neutralization, it involves the reaction of an acid and a base to form 1 mole of water, which I've just been through. And the value of all neutralization reactions are the same. So they will all be minus 57 kilojoules per mole. Okay. Now, this is just to consolidate your knowledge on standard state pressure and temperature. So I'm going to start this poll. Relaunch. Continue. Okay, I hope you can see the poll. So once you think you know the answer, vote for it, and then I'll end poll and I'll see if you got it. Yeah, all right, sweet. So that's C. You got it correct. Well done. Right, next we're going to go through measuring enthalpy change and using the Kelvin scale of temperature. So that's when we went through the 298 Kelvin. The Kelvin scale starts at absolute 0, which is equivalent to minus 273 degrees centigrade. That's quite an important conversion for you to remember. So 0 Kelvin is equivalent to minus 273 degrees centigrade. So for whatever value of Kelvin you have, if you want to convert it into degrees centigrade, all you do is take that number and minus 273, and you'll get the equal conversion to Kelvin. On the Kelvin scale, ice melts at 273, which is, as you know, ice melts at 0 degrees centigrade and water boils at 100 degrees centigrade. So using that minus 273 from whatever you want to do, ice melts at 273 Kelvin, okay? And then water boils at 373 Kelvin. Actually, let me correct myself. To get from degree centigrade to Kelvin, you need to add 273, not minus 273, because if you see, so you've got minus 273 degrees centigrade, and to get to 0 Kelvin, you'll need to add 273 to get to 0. Okay, that's one thing to remember. They're equivalent in terms of the scale. So 1 Kelvin rise in temperature is the same as 1 degrees centigrade rise in temperature. When doing experiments, or if you've got an exam question and they've given you values for the temperature change, the thermometer, they're usually graduated in degrees centigrade. And so the temperature change that you see in degrees centigrade is exactly the same as the temperature change in Kelvin, because we've got this unity here, 1 Kelvin and 1 degree centigrade. And so calculating an energy change requires knowledge of the surroundings, right? What the surroundings include. And if you remember, the surroundings are relevant for exothermic, endothermic reactions, change of delta H, which is change of enthalpy. And so we're just building on the knowledge that we've started with. So the energy change of the surroundings is calculated from 3 quantities. So you've got mass, specific heat capacity, which is a standard, it doesn't change, it's just a value, and then the temperature change, which you'll get, okay, from the thermometer. Now, if we go through, so the mass of the surroundings is simply measured by weighing whatever you have in the reactant. And then you have to identify the materials that are changing in temperature, right? So that's just the equation. If you have your equation, you'll see what the mass is. And if you have your products, you'll see which of those elements are changing, which the materials that are being produced to calculate your change in energy of the surroundings, your energy change of the surroundings. The specific heat capacity. So different materials require different quantities, different amounts of energies to produce the same temperature change. And the specific heat capacity, which is denoted by C, is the energy required to raise 1 gram of a substance by 1 Kelvin. And every substance has a specific heat capacity. So for water, the specific heat capacity is 4.18 joules per gram per Kelvin. So usually, I believe you just need to remember the fact that C is 4.18. I don't know whether they give you that in the exam because I think different boards do different things. And the temperature change of the surroundings is delta T. I don't know why they put A there. And this is determined by the thermometer readings, as I've just said in the slide before. So delta T equals the change, the temperature at the end of the reaction minus the temperature that at the start of the reaction. So at the beginning of the reaction, that's your base temperature. Then when the reaction is finished or at the peak, the highest point of the reaction temperature-wise counts as the final temperature. Find the difference, you find the difference in temperature, and that's the temperature change in surroundings. From this, we get to a very important equation, which is calculating the energy change denoted by Q. So Q equals MC delta T, and this is measured in joules. So Q is in joules. It could also be in kilojoules if they ask you that as well. When I was doing this, we always remembered it as Q equals MCAT because the delta looks like an A. And if that works for you, you can remember it, Q equals MCAT, and that will get you MC delta T. So now determining the enthalpy change of combustion, right? So this is calculating it. We know that combustion is a reaction of a substance with oxygen, and this is one of the easiest enthalpy changes to determine. So we're going to start with that. Looking at the combustion of methanol, you've got CH3OH plus 1.5 oxygens goes to CO2 and 2H2O. And you'll recognize this as an example of what we just did before with the balancing of the equations. You've got 1 mole of that here. Yeah, that's the end of that slide. Okay, so in terms of the accuracy of this value, there are different reasons that you may get a different value from a data book than if you do an experiment, and you need to know what these possible differences, how these can come about. In an exam question, it might ask you describe, list, explain the possible reasons for difference in a data book value and an experimental value. One is the heat loss to the surroundings other than the water. So when you do this, I'm not sure whether you've done it in school yet, but if you do this experiment, usually when you're measuring the temperature change, it's the test tube is open sometimes, so you can get heat that emanates from the solution. And so this counts as heat loss to the surroundings other than water, which means that it won't affect the final temperature, which it should. You have incomplete combustion, so the reaction does not fully take place, and this means that not all of the reactant has reacted, which means that you won't get the proper value, which is seen in the data book. Next one is evaporation from the wick, pretty self-explanatory. And then if you do not have standard conditions, so obviously if you're doing an experiment, it's quite hard to make sure that you have your standard conditions. And these would lead to a value for delta CH that's less exothermic than expected because you've got energy losses in these four things. We'll go for things. And so these are very important to note down, try and remember so that you can like whittle it off if you have an exam question like this. I think I might as well explain the evaporation from the wick. So the burner must be weighed as soon as possible after you finish using the flame, because then some of the methanol may have evaporated from the wick. And so it depends what burner you're using. So sometimes spirit burners have a cover which reduce this error. So I'm not sure what burners you have, but on some of them, if you turn, there's a little like ring thing at the bottom. If you turn it to cover the hole, then it reduces this error. So we're going to go through a practice question and we'll go through it slowly so that you can make sure you've got your understanding. So for an experiment, say I did it, I measured the mass of the spirit burner and the methanol before burning, and that came to 196.97 grams. And then once the experiment is done, I measured the same thing again, which was 195.37 grams. And as you can see, the change in mass is 1.60 grams. Okay, you don't necessarily need to know the mass of the spirit burner because it's in both, so it cancels it out in terms of the difference. Now you've got your initial temperature, which is 21.5 degrees centigrade, and your final temperature, which was 62.5 degrees centigrade, and the temperature change therefore is 41.0 degrees centigrade. If you remember what we said before, this is equal, it will also be equal to 41 Kelvin because the temperature change is exactly the same. And so for water, as we said, if water has a density of 1 gram per centimeter cubed, C will have your standard value of 4.18. Then we've got the equation which we've been through, calculating energy change, Q equals MCAT in joules. And so we've got the energy change of water, the energy change Q, you've got 150, which is your mass of the water, right? So that's 150. That's just, it will give you that value. You'll know that in the experiment. Times 4.18, that comes from the water density, times 41, okay? And that comes from temperature change, right? And then you get to 25,707 joules, which then if you do your conversions, it comes to 25.707 kilojoules, okay? As we can see here, you should always leave rounding figures to the final step. Otherwise, you may get inaccurate results. And that's just a good tip for all calculations that you do in life, really. Make sure you always leave rounding to the final bit so that you don't get, because then if the calculation is more complicated, you've got various steps and you keep rounding and rounding and rounding and rounding, you're going to get further and further away from the right result. Now, from this, you need to calculate the amount in moles of CH3OH, which is burnt, all right? And you should know that moles equals mass over MR. And remember, we have the mass from here. We calculated that mass, okay? And so we use that. Mass is 1.6, and the MR you can calculate using the periodic table, which if you do that, you'll get 32. And then you can get the moles of CH3OH burnt, which is 0.05 moles. Next would be to calculate the combustion thing. Here, do that properly. And as you know, the definition is the enthalpy change for the complete combustion of the reactant that they gave us. This is the reactant that they gave us. All right, so it's 1 mole of that. In the experiment then, we've got 0.05 moles, okay, transfers this amount of kilojoules of energy to the water, right? So then we've got 0.05 dot goes to, goes to 25.707. All right, so the water gained 25.707 kilojoules of energy from the combustion of 0.05 CH3OH. All right, and from this, we need to calculate from 0.05 moles to 1 mole. Okay, so how you get from 0.05 moles to 1 mole is the same as how you'd get from 25.707 to your actual value of whatever you need. Okay, and so since it's 1 mole, if we're starting at the equation, it will be 25.707 divided by this, okay, to get this value, right? And that comes to 514.14 kilojoules. And therefore we can say that the standard combustion enthalpy change of CH3OH is equal to 5,000, that should be 514.1 per mole. Okay, there should be a point here. Okay, right. And since it's combustion, it's an exothermic reaction, and so the energy change is minus. Remember that as well, okay? Now we're going to do a practice exam question. So here you read it, okay? A student carries out an experiment, right? This may be important later if they ask you, why is it not textbook figure, to determine the enthalpy change of combustion. Okay, so we're looking at combustion here of glucose, right? In the experiment, 0.831 of glucose is burnt. Remember, that's used for the second part of this calculation. The energy released is used to heat 100 centimeters cubed of water. And they've given you, there we go, okay, good. They've given you the specific heat capacity of water there, all right? The energy release is used to heat 100 centimeter cubes of water from 23.7 to 41 degrees Kelvin. Calculate the energy released in kilojoules, okay, during combustion of 0.831 grams of glucose. I'll let you get on with that, and then we'll go through it and answer any questions if you do have them. Let me know in the chat when you're done. Just a heads up, whilst you're doing this, read the question very carefully, okay? So this is asking you to calculate the energy released, okay? That's all it's asking you to do for now, is calculate the energy released using one of the formulas which we've just gone through. And then there are a few questions after that which again, read it so that you can answer that specific question, only what they're asking at the time that they're asking it. Okay, brilliant. So hopefully you, well, let me just find my page. Where's my page? Oh there. Okay, there we go. So hopefully you got your 100 centimeters cubed of water, and you times that by your 4.18 specific heat capacity, and then you times that by the change in temperature, which is 17.3, which should have given you 172. No, sorry. I'm getting my dyslexic numbers mixed up. 7, 2, 3, 1 joules, which then you converted to kilojoules, which should, as we've come back, where should I go back to? As we've come back here, so remember the conversion from joules to kilojoules, the way I remember it is you just go back 1, 2, 3 decimal places. Oh, hold on. 7, 2, 3, 1.4. Yeah, correct. So there, and then you need to go back 1, 2, 3 decimal places. Okay, and you should have 7.231. Did you get that? Yes, brilliant. Okay. Sorry about that. Right. Now we have two more questions. Calculate the amount in moles of glucose that is burned. That's the second step that we did just before. And then calculate the enthalpy change of combustion of glucose and give your answer to 3 significant figures. Okay, so this is just completing the calculation which we did before, the same application. See if you can do that and let me know once you're done, and then we'll go through the answer. Let me know if you want to move forwards as well. Yeah, sweet. All right. I'm going to go through the answers. Are you nearly done? Yep. Okay. So for this equation, you should have got the molecular weight as 180. And then the calculation is 0.831 divided by 180. And that should give you your number. And then you need to times that by, sorry, and then that should be 4.62 times 10/3. Did you get that answer? What was your answer? Okay, brilliant. And then calculate the enthalpy change of combustion of glucose. Give your answer to 3 significant figures. Sorry. Then you use your answer before, 7.231 divided by your 4.62 times 10⁻3, and you should have got 1. Actually, what was your answer? You don't need to put the these in, just give me the number. If you didn't get it, that's fine. We can 1721.67. Okay, that it should have been, so you've got 7231 divided by 4.62, which should have been 1560, I believe. But that's fine. Obviously, this is recorded and we can go over that, or you can go over that question later. I'm afraid we're going to have to move on. We have some more practice exam questions. And so it's defined the enthalpy change of combustion. Okay. For the, in the interest of time, I'm going to just go through the answer for this, because this is more about exam technique than anything. You can remember, commit it to memory, the enthalpy change of combustion anytime, but I'll go through the mark scheme because that's probably the most important thing in terms of this question. So this was 2 marks, if you just saw there. The first mark is for saying the enthalpy change for the complete combustion. So that's one thing. So you need to remember complete combustion, enthalpy change of complete. You already have enthalpy change here, but remember it's complete. Okay, that's important. Complete combustion of 1 mole of a substance. That's the next bit. Okay. And here you can see that it will allow energy change for combustion in excess oxygen. So this is probably the easiest easiest bit to do. But some people put excess oxygen because that means that the combustion is complete. Okay. Make sure it's not energy required. Okay, because it's not the energy required, it's the enthalpy change. All right. Now, next is a student carries out an experiment to determine the enthalpy change of combustion of pentan-1-ol. In the experiment, 1.76 grams of that was burnt. The energy was used to heat 250 centimeters cubed of water from 24 degrees centigrade to 78 degrees centigrade. Calculate the energy released in kilojoules during combustion. Again, this is the same application as we had 3 3 questions ago. Would you like to do it, or shall I just go through the mark scheme? It's completely up to you. Go through mark scheme. All right. Well, there's not really a mark scheme, but it gives you the answer, 56.430 kilojoules. And it will just use the same equations before, which should be Q equals MCAT. Let me just write that there. Q equals MC delta T. Okay. And then you just plug in the numbers and you should get that answer. Now, the next question is write an equation for the complete combustion of propanone to form carbon dioxide and water. This is relating to something we did earlier on. Complete combustion, standard conditions. It's just another application of that. Again, I'll just go through the mark scheme. So then you end up with C3H6 plus 4 oxygen, which goes to 3 CO2 plus 3 H2O. And then we move on to the third bit of the question. In a lab experiment, 1.45 grams of propanone were completely burned in oxygen. The heat raised the temperature of 100 grams of water from 239.1 Kelvin to 351.2. So the important bits here are 1.4 grams burned completely. So you know it's complete combustion. And then this is 100 grams of water from, and then you calculate the difference there. Here, remember, read the question carefully. Just don't go into automatic mode and try and calculate the enthalpy change. Calculate the number of moles of propanone in the 1.45 grams. This is just moles equals mass over MR. And there we go. So you should have got you would get 0.0250. Next, it's calculate the heat energy required to raise the temperature of 100 grams of water from 293.1 to 351.2. And it gives you the specific heat capacity of water. And from here, you use MCAT. Then you get 100 times 4.18 times 58.1. And then that would give you 24.3 kilojoules. Here it says if 1.45 is used instead of 100, then you'll get 0 marks. Okay. The third part of the question is calculate the value in kilojoules per mole for the enthalpy of combustion of propanone. Then you use the 2 values you got, 24.3, divide it by 0.025, and you should get minus 972 kilojoules per mole. Remember, combustion exothermic, you get minus, and also remember your kilojoules, it's asked you for kilojoules, so make sure your answer is in kilojoules. Next is another question. This should be the last one, then we'll move on to another experimental determination. In a similar experiment, the enthalpy of combustion of butanone was found to be minus 1290 kilojoules per mole. Databook value for the same reaction is minus 2430 kilojoules per mole. Suggests one reason why the experimental value is very different from the databook value. And then you just mash out one of those 4 points that we covered earlier. So here you could say heat loss or energy loss, and that would have given you the mark. Next, we'll go over determining an enthalpy change of reaction. Okay, so there are many reactions that take place between 2 solutions or between a solid and a solution. The enthalpy change of these reactions can be determined in a lab at school using plastic cups made of polystyrene foam. This is because basically they're cheap, they're waterproof, they're lightweight, and they offer some insulation as well, which will limit the heat loss of the reaction. Okay. just know that obviously the thermometer in the solution will record any temperature change, which will allow the heat energy to be calculated using MCAT, which is the same application that we used before for the questions which we just did. Bear in mind that when we're carrying out reactions between aqueous solutions, the solution itself is the immediate surroundings, which means that is what you need to measure in terms of temperature change. This would be an exam question. So in excess of zinc powder is added to 50 centimeters cubed of 1 mole per decimeter cubed of copper 2 sulfate. The mixture is stirred until a maximum temperature is obtained, and that would be the final temperature, which you use to calculate the difference. Find the enthalpy change of reaction and then it gives you the equation, which is very helpful. Gives you initial temperature of solution, final temperature of solution. It does the temperature change for you, and then it gives you the value of C as well. We can go through the answer again because it's the same application which we did. So first thing is you do Q equals MC delta T, which gives you 7.942 kilojoules. Next is to calculate the amount in moles that's reacted with zinc. And again, so this is similar to the combustion. Zinc is in excess as oxygen would be in excess in combustion. This makes sure that the reaction is complete. Okay. And then, so moles equals mass over no, this is an aqueous solution. Okay, so it's density times volume. You should know that equation as well, which is used to calculate moles in an aqueous solution. Okay, so that's different to moles equals mass over mR. This is moles equals density times volume. And then you should get 0.05 moles. Bear in mind, you've got decimeter cubed here, okay, because that's part of the equation. And here you've got centimeters cubed. So you'd need to convert that to the correct value. Next, it's calculates the enthalpy change in kilojoules per mole for the reaction. Now, remember, we need 1 mole, okay, 1 mole of this. Luckily, when they gave you the equation, it's all balanced out, which gives us 1 mole automatically. Sometimes they might give you a reaction in which they'll have 3, 4, 5 moles of the molecule that you are required to calculate. Then you'll just need to balance the equation so that you only get 1 mole of whichever molecule it's asked you to calculate. And you'll get the answer as 159 kilojoules of energy, and then you get the enthalpy change as minus 159 kilojoules per mole. All right. Now, the next one is determining the enthalpy change of neutralization, which again, we went through the theory just before, is very similar. So a practice question would be, student measures out 35 centimeters cubed. So bear in mind, this is centimeters cubed. Again, you'd need to change to decimeters cubed. Stuff with these exam questions, the process method of doing them is very similar. So the more and more you do, the quicker you'll get at them. But what you do need to make sure that you look out for is the centimeter cubes, decimeter cubes, joules, kilojoules, and all of that stuff. And then it gives you specific heat capacity and asks you to calculate the enthalpy change of neutralization. So remember, it's 1 mole as well of water. So the answer, we calculate the energy change. So from here, we can find the total volume of solution, right, which is 35 and 35. So this is something to remember with neutralization. You've got 2 aqueous solutions, which means your mass will be the summed result of both of them. And here we have 35, and here we have 35 as well. Okay. Next is calculate the amount in moles. of NaOH and HCCI that reacted. And you should get the answer of 0.840. Obviously, you can go through that later because it's a simple equation which you should be able to do. Next is the change, enthalpy change of neutralization. And so here we've got the equation, okay? And again, they've balanced it out to get 1 mole of water. And again, it works out quite nicely because this is the entire equation. You don't need to change anything. And this means that they're all 0.0840 moles, right? Because the moles are the same. If this said 2, for example, as we said before, you'd have to double that, okay? But they're all the same. Now, the formation of H2O transfers 4.8279, which is what we got here, of energy from the solution. So the formation of 1 mole of H2O loses, then we've got this number divided by this number, and then you'd get 57.5 kilojoules. And remember, it's exothermic, so we have minus, okay? So for example, again, so if we had, not that it works with this equation, but say we had 3/2 here, and we had 2 here, and you knew that 3/2 moles, or no, let's just make it simple. Say you had 1 there. So you know that 1 mole of 0.0840 is 1 mole. So 2 moles of H2O here would be double that. And then you'd have to use that in this equation here for that value. You won't use 0.0840. You'd have to double it and then slot it in there. A lot of people forget that and they just use the moles that they calculated here, which is not, as you can see, of water. It's not the moles of water. So you need to make sure you calculate that properly. Right, what time is it? Yes, okay, so we'll have a lunch break now. It's currently 12:12 or about 12:10. And we will come back at, so we'll come back at 12:45. Okay, so set an alarm. We'll come back at 12:45. And then we will start with bond enthalpies. And then we'll move on to Hess's law and enthalpy cycles, and then rates of reaction, and then Boltzmann distribution. So we've still got quite a lot to go through. Again, if you have any questions when we come back, make sure you type them up in the chat, and then we'll go through them before we start. And yeah, the bond enthalpies are quite simple, so we can power through that and go through some questions of the later ones, which are a little bit more complicated. All right, sweet. So I shall see you at 12:45. Have a nice break. Bye. I apologies, just had to sort something out. Are you back? Cool. All right. So we will start with bond enthalpies now. We'll look at how an average bond enthalpy can be used to calculate enthalpy change of a reaction without carrying out any experiments and just using data given in booklets and so on. All right. So bond enthalpies. The average bond enthalpy is the energy required to break 1 mole of a specific type of bond in a gaseous molecule. Bear in mind, this is always a gaseous molecule, even if this molecule is naturally in a solid or liquid state. Energies always required to break bonds, as I've said before. Bond enthalpies are always endothermic because energy is required to form them. And bond enthalpies, therefore, because they're endothermic, have a positive enthalpy value. These are just examples of bond enthalpies and how they'll be shown in an exam question and probably in your textbook as well. So the limitations of average bond enthalpy, so the actual bond enthalpy can vary depending on the chemical environment of the bond. But then the bond enthalpy that will be given in tables are under very strict conditions. So do not, and so obviously if the chemical environment changes, which it would in the natural state, it's not entirely accurate in, it doesn't apply to all chemical environments. So the average bond enthalpy is calculated from the actual bond enthalpies in different chemical environments. Okay, so in calculations, you'll be provided with average bond enthalpies, and we'll go through bond breaking and bond making. So in chemical reactions, as we said before, bonds will have to break and then new bonds will have to form to create the molecules, the products. And here we can see another similar graph. We have H, which is enthalpy. And then what we've got here is the start. So this line here would represent the products, okay? The reactants, sorry. This would represent the reactants, the start of the experiment, the start of the equation, the left-hand side. And then when bonds are broken, all right, it's, for an example, for this, it's exothermic. Energy is required to break bonds. That's always the case. As you can see here in the endothermic one, energy is required to break bonds. And making the bonds in an exothermic reaction, energy is required, energy is released when they make the bonds, as it's greater than the energy required when breaking the bonds. Right, and then here, obviously, you have delta H, and it's negative, which means it's exothermic. And then on the contrary, you have endothermic reactions where you've got the breaking bonds and making bonds. And here you can see delta H is positive. The energy required when breaking the bonds is greater than the energy released when making the bonds. So it's basically the size of this against the size of this. So because making the bonds is greater, it's exothermic, and the size of this and the size of this. So breaking the bonds is larger, greater than making the bonds, which makes it endothermic. That's exactly what I've just said. So the difference between the energy required for bond breaking and bond making determined whether an overall reaction is exo or endothermic. So we'll go for calculating enthalpy changes from average bond enthalpies. The enthalpy change of a reaction, denoted by that, can be found by calculating the bond enthalpies of the bonds in the reactants and the products using the values given to you. For a reaction involving gaseous molecules of covalent substances, delta RH is the sum, that means sum, I'm sure you know that, the sum of bond enthalpies in the reactants minus the sum of bond enthalpies in the products. So it's quite a simple, just addition, subtraction, all of that, but it can get quite complicated if it's a lot of molecules and a lot of bonds. So it's just something you need to, it's very easy, but you need to concentrate on it. So this would be a practice question. Using average bond enthalpies, calculate delta RH for the reaction of propane with oxygen. So here we have CH3, C3H8 plus 5O2 goes to 3CO2 plus 4H2O. And it's given you all the values that you might need here. We obviously don't need all of them. Oh, my bad. But you'll need some of them. Okay, so this is the equation here. It's been given to you. And then if you draw it out, it's much easier to visualize the bonds, right, that are in each of the molecules. Okay. And so extending the table, this is one way you can do it. Extending the table, you have the equation here, you have the visual construct here, and then this will be bonds broken. So you have 8 CH bonds that are broken, 2 CC's bonds that are broken. Here you can see 1 and 2. And then 5 oxygen bonds that are broken. Well, you can see 1, 2, 3, 4, 5. And then in forming in the products, 6 CO bonds, these CO bonds are made, and 8 OH bonds are made. Yeah, so remember, these are broken and these are made. Move that away. So it's a charge. All right. And extending the table again, this is where we have calculations. So you have 8 bonds being broken, which is 413, which you get from this table here. Okay, it says 413. And you apply the same, it's the same application for each of these. So these are bonds broken, bonds broken, bonds broken, and bonds made, and bonds made, right? So then you have 6, 4, 8, 8, and then 8, 5, 4, 2. And so delta RH ends up as 2054. And that's it. Now, question. Bond enthalpies always have a positive enthalpy value. Okay, this means that they are A, endothermic, B, exothermic, C, covalent compounds, or D, the bond enthalpies are happy. All right, so I'll relaunch that and you can pick an answer. Yes, good. Endothermic, brilliant. All right, we'll move on. So here it's just another exam question. Use this data to calculate the enthalpy change for the following gas phase reaction between hydrazine and hydrogen peroxide. Remember, in terms of delta RH, it's always gas phase, okay? And here you just apply the same knowledge, okay? Sum of bonds broken minus sum of bonds formed is equal to, and they've calculated it using the table that I said before, and it's come up to 789. Yeah. Now, another practice equation, this equation below shows the combustion of methanol, CH3OH, in the gaseous state. And it's given you the equation here. Using the average bond enthalpies in the table above, calculate the enthalpy change of combustion of gaseous methanol. Okay. This, let me just look at this, right. Well, probably the hardest thing about these questions is going from that, okay, to to visualizing, okay, to visualizing the compounds. So I shall leave you this question and then let me know once you're done. It's quite a long question. So let me know once you're done or if you have any questions. All right, just in the interest of time, I'm going to go through the answers because basically the most important part of this these questions is making sure you've got the visual compounds correct. Okay, so you've got the equation here, and it should have come out as this. Okay. Oh, and the moles also count. So as you can see here. Okay. So you need to include that in your calculations. So you should have come up with this visual diagram, and then you can calculate then using the average bond enthalpies that they've given you and come up with -689 kilojoules per mole. The limitations of bond enthalpy, the average bond enthalpy is different to actual values depending on the environment. And calculations using average bond enthalpies need all species to be gaseous molecules. So again, these are one of these exam questions where they will just ask you to state it, and you'll have to remember and just write it out. You're not having a brain now. Hess's law and enthalpy cycles. So Hess's law states that if a reaction can take place by two routes, and the starting and finishing conditions of those two routes are the same, then the total enthalpy change is the same for each route. Okay, it makes sense when you visualize it. So yeah, I'll just start here. Right, so here you have reactants, okay, you have products, okay, and here you have an intermediary, okay. So to get from reactants to products, one way is this is one reaction, and then this is the second reaction, okay. And so writing it out, you have route one, which is reactants to A, and then A to B. So that's one of the routes. Second route is straight from reactions to products. Now, if only the enthalpy changes of A and B are known, again, using simple maths, you can calculate that by Hess's law, the total enthalpy change is the same for each route. So A plus B would equal C. If two of A and B and C are known, then the third can be calculated. Using this, you can just rearrange. So if B and C are known and you want A, then you can just rearrange this for the same one. So here you should calculate value C based on Hess's law. So here you have this this enthalpy change and then minus 150. Again, using the same thing, you can A plus B equals C. So you've got 110 plus minus 150 equals C, which is minus 40 kilojoules per mole. This principle can be extended for any number of enthalpy changes, which is probably the most complicated thing about this principle, is that they can give you a graph like this with 4 or 5 or 6 different lines everywhere. And then you'll have to carefully go through each of them, find a route that they want you to find, and then use and then calculate it correctly. The pluses and the minuses are one of the things that throw a lot of people off when they do these questions. Now, provided that all enthalpy changes are known except for one, the unknown enthalpy change can always be determined. Now, we have indirect determination of enthalpy changes. The most useful values are for standard enthalpy change of formation and combustion. Enthalpy changes can be used with Hess's law to determine enthalpy changes indirectly. You can work out the standard enthalpy change of any reaction from these formation and combustions of the reactants and the products. So this is an example, calculating standard enthalpy change of formation from these values here. Okay. You can work this out using enthalpy change of formation. So here's an example. Calculate the standard enthalpy change reaction for the reaction shown below. Here's the reaction shown below. Okay. And it's given you standard enthalpy change of formation for each of them. Okay. And as you remember, these are just elements, so they do not have standard enthalpy changes. And so from this, it might ask you to construct the enthalpy cycle between the reactants, which are these, and the products, which is this, and the elements, which is Fe, Ca, and also remember that oxygen is an element in this equation, so you can't forget about oxygen. The reactants and the products of the original reaction are formed from the elements, and the arrow points upwards. So this is how we do it. So you have the original equation that they gave you, and then you've got all the elements at the bottom, and then you've simply got the elements making this side and the elements making that side. And these are formations, right? And from this, we can say that elements that form the reactants is B, and then the reactants forming the product is A, right? That's route one. And route two, so remember, it's all about the products. And then route two is the elements just straight up making the products. And by Hess's law, B plus A is equal to C. All right. And so using the same thing, A, okay, here is equal to C minus B. Now, using this, we can add and calculate the unknown enthalpy changes. So if we want to try and calculate A, we have 3 times minus 635 because there's 3 of these. And then minus 824, which is this. Okay. Equals minus 1081. The reason we're not including this and this is because their standard enthalpies are 0, since all elements standard enthalpies are 0. Now, this is another example. Calculate the standard enthalpy change of combustion for the reaction shown below. So we've got 4 carbons plus 5 hydrogens get to C4H10. Okay, so from this, we've got 4 carbons plus 5 hydrogens go to C4 plus 10, C4H10. And from this, we have the combustion product. So this is no longer using, this is no longer using elements. Okay, elements are for formation. And you can use the same principle to calculate from combustion. Yeah, so these are now standard enthalpy change of combustion because you can see the little C right here. And so combustion products, as always, we stated that combustion products are CO2 and H2O, right? And then you do the same thing for combustion. Remember, it's these going to the combustion products. Okay, that's why the arrows point downwards. And then for the formation, remember, it's upwards for formation. But for combustion, because something needs to happen, they need to react with oxygen. That's another reaction here. And again, so then you have root 1, which is A to C, and root 2, which is B. And by Hess's law, you can say that A plus C equals B. So A equals B minus C, because to get to A, you need to go this way and that way. And this way is going along the line of B, and upwards, we're going against the line of C. So whatever value they give us for C is going against it, so you'll need to minus that. And so they will give you the numbers here, which are from 2 tables ago. And then you can say that A, which is this one, is B is 4 times minus 394 plus 5 times minus 2686 minus 2877. So because this is minus 2877, but we're going against the line, okay, it gets minus, which obviously equals plus, and you end up with 129 kilojoules per mole. This is another example. Calculate the value for the standard enthalpy of formation for the liquid, whatever that is, ethanol. Use the equation given below and enthalpy of combustion data from the following table. So this is combustion, okay? And it says, they're trying to confuse you here, okay? Because it says standard enthalpy of formation and standard enthalpy of combustion. But if you look, if you look at the equation, this is the standard enthalpy of formation, right? So they've only said that because that's what the original equation is. And so using this, you've got, so you would draw a line here and a line here, and you have CO2 and H2O. That's meant to be, that's very bad. And so here you've got CO2, H2O, and then also remember that this needs to be combusted. Okay, so that needs to react with oxygen as well, and that ends up with SO2. And then you've got these as well. going up to C2H5SH. Okay, and then you calculate, if you basically plug in all of the numbers, and this is where I said it gets a little bit complicated because you need to follow the arrows. Yeah, so we're going with the arrow here because it's a plus, with the arrow here because there's a plus there, with the arrow here is a plus there, and then minus against these arrows. Okay, and that means it's obviously plus, and you end up with 773. But make sure you show your workings because you only get a third if you just put 773. You can show your workings using one of these cycles instead of writing everything out like that, as long as you write down all the calculations. Now, this is another question. The standard enthalpy change of combustion of glucose can also be determined indirectly. Calculate the standard enthalpy change of combustion. So that's what you're calculating, combustion of glucose using the standard enthalpy changes of formation below. And they've given you, this is the combustion equation. That's what you're calculating this one. That's what they've asked you to calculate. And then it's using the standard enthalpy changes of formation. So here we've got carbon, we've got hydrogen, and we've got oxygen. Those are all of the elements we have here. Okay. And then using this, they've given us the, oh yeah, anyway, sorry. That's a question in its own. So this one you need to be careful because the values are for formation. So we'll need to draw a formation cycle, as I just said. And the correct answer would be, if you do want to calculate it, it's 1, 2, 5, 0 kilojoules per mole. Yeah, you can calculate that later. And remember, when you're doing the cycles of formation, the elements would be here, and the elements form this and form that. So bear in mind which way the arrows are going. Now, these are some other questions here. Some standard enthalpies of formation are given below. Remember, it's formation. So here, if I do it simply here, you've got N2, that's H2, sorry, and N2 formation to N2 H4. Okay, and then that arrow there would be plus 75. Yeah, so it confuses a little bit when they just give that value. People need to remember that it's from the elements to that value. So then it says state the value of delta HF in standard conditions for N2 in the gaseous state. Would you like to try it, or shall I just go through the mark scheme? You can just put it on the chat. Mark scheme. Okay, so for the first one, it's 0, okay, because this is an element, remember? So elements have no delta H, no enthalpy change of formation, because they are elements. And now use delta HF values from the table over here to calculate the enthalpy change for this reaction. And so the enthalpy change, the sum of enthalpy changes of formation of products minus the enthalpy changes of formation of reactants, because so if elements are down here, we're going from here. Okay, remember the arrow is up here to here. So we're going against the arrow here and with the arrow here, which is Y. they have the minus 247 over here. And the minus here as well. And you end up with minus 777. So a summary with this would be that there are two rules that you can use to help you with your calculations. It would be enthalpy change of formation and enthalpy change of combustion. Just remember that with formation and with combustion, with formation, the arrows go up, and with combustion, the arrows will go down. All right. And there it just gives you a lot of symbols, but makes sense if you know everything. So that just means sum of, and that just means delta CH, which we've already done. And that's delta RH, which is the enthalpy change of the reaction. No. Okay, what needs to remain the same for Hess's law to apply? I'll do a little poll, relaunch, continue. Is it A, conditions, B, enthalpy, C, endoscopy, or D, the orientation of the molecules? Conditions, yeah, correct. All right, good. We are now going to go on to rates of reaction. So I think we should be good for time. Hopefully, Boltzmann distributions are later, and I'd like to cover that quite thoroughly. So rates of reaction first. So what's meant by rate of reaction? The rate of a chemical reaction measures how fast a reactant is being used up or how fast a product is being formed. So the rate is calculated by change in concentration over time. And that change in concentration is how fast the reactant is being used up or how fast products being formed. And the units are moles per decimeter cubed for concentration, and then time in seconds, which gives you this. Make sure you're careful about the decimeter cubed and the seconds as well in exam questions. Yeah, I've just gone through that. Now, the rate of reaction, this is a concentration time graph, and this shows you the rate of the reaction. Well, actually, no, it can be used to monitor. So here we have, this is the change in concentration, okay? And this is the time. So you can just plug in the numbers from any certain point, and then from this equation, and it will give you the correct answer. Now, in a series of, this is a question, in a series of experiments to investigate the factors which control the rate of a chemical reaction, aqueous hydrochloric acid was added to calcium carbonate. So we have aqueous hydrochloric acid, calcium carbonate, and a conical flask placed on an electronic balance. The loss in mass of the flask and its content was recorded for 15 minutes. So here we have time. Okay, 4 experiments were carried out. 1, 3, and 4 were carried out at room temperature. This may be important. The same mass of calcium carbonate was used in each experiment, so it's the same mass. The piece of calcium carbonate were the same size as well. So that gives you the same surface area. Now except for this one, which is one large piece, obviously less surface area. So in experiment 1, this is standard, the standard conditions for this experiment. So, and as it said, 1, 3, and 4 were carried out in room temperature, but as you can see here, 2 was heated to 80 degrees centigrade. Okay. And so the results of experiment 1, which is small pieces at 50 centimeters cubed of 1 mole per dm cubed. So it says, explain why there is a loss in mass as the reaction proceeds. This is a fairly simple answer. Okay, if you know what's going on, you look at this here, right? You've got solid, you've got aqueous, you've got a liquid, and then you've got a gas. the only thing that's going to reduce the mass is going to be the gas, because that's floating off somewhere. And so the loss in mass is because carbon dioxide escapes from the flask. You need to know, you need to say from the flask and just escape from anywhere. Then it says, explain the shape of the curve drawn for experiment 1. Again, this is just knowledge of experiment and application of your general knowledge of chemistry. All right, so the reaction is as fast at first, as you can see here, and then it slows down. You're just describing this curve. And then, but you need to know that when the line is horizontal, the reaction has finished. You know the reaction has finished because the mass loss does not change. And you can probably just estimate when that is. It says after 6 or 7 minutes, or you can either use time, or you can use the mass lost, or whatever's on that axis. And here it says, draw curves on the graph to represent the results you'd expect for experiments 2, 3, and 4. Okay. And so using your knowledge, again, of surface area, of heat, and of concentration, which is the same except for this one. Okay. So you should make sure you know all of those. You should be able to draw curves on the graph that show this. So experiment 2, we look at this. It's small pieces, same as, so this experiment, we're comparing all of these to experiment 1. All the conditions are being compared. Small pieces the same. 50 the same, 1 mole per decimeter cubed is the same, but it's heated to 80. Okay, so it should be steeper, but then balance off at the same point. Now, experiment 3 is 50 the same, 1 the same, no heating, but instead it's 1 large piece instead of lots of small pieces. Now, because the surface area is reduced, it would be less steep, and also possibly the reaction might be incomplete, and there's the same mass loss. Now, experiment 4 is small pieces, 50, but 2 moles per dm cubed. Concentration is doubled. And if concentration is doubled, then it's going to be steeper. If, they're small pieces and the concentration is doubled, it's going to be steeper. And the concentration means that the horizontal should be twice the mass loss. So there should be 2 up here. Okay. And it's just comparing what has been given and using your experimental knowledge of chemistry to answer these questions. Now, this is calculate the mass of calcium carbonate, which exactly reacts with 50 centimeters cubed of 1 mole per decimeter cubed of aqueous hydrochloric acid with an MR of 100. Okay, here is you use all of the calculations, formulas that you know. I'll go through the mark scheme. So you have 50 centimeters cubed of 0.1 moles per decimeter cubed, right? Make sure you've got that and that sorted out, okay? And you want to calculate the moles. So that's 50 times 1/1000. And that should give you 5 times 10 to the minus 2. And so you know how many moles have reacted, right? Because we've cancelled that and cancelled that. And then this reacts with half the amount of moles of CaCO3. So if we go back to the equation, okay, now we've got this is 1 mole and that's 2 moles, okay? So if we look at this question again, they've given us hydrochloric acid, which is 2 moles, okay? So this is double the amount of moles of calcium carbonate. So to calculate the moles of calcium carbonate, you'd need to divide it by 2. So make sure you remember that in all the exam questions. Always go back to the formula if you're not sure. And then you use moles equals mass over MR, rearrange it, and then you can find the mass and make sure you've got your units and your method as well, as it says. Now, altering the rate of a reaction, as before with your knowledge of experimental chemistry, that's what we're going to go through now. So the factors that can change are concentration or pressure when it's gases, temperature, use of a catalyst, surface area of solid reactants. So obviously if this increases, rate of reaction increases, or if pressure, pressure is the same, temperature increases, rate of the reaction increases, use of a catalyst increases, chemical reaction increases, and surface area, if there's a higher surface area, the chemical reaction would go faster. So this is another something that you'll just need to write down, memorize, and be ready to parry off if you have an answer, if you have a question like that. To explain this, we can use collision theory to explain why some collisions are effective and why others aren't. So the collision theory states that two reacting particles must collide for a reaction to occur. There's usually only a small proportion of collisions result in a chemical reaction. And this relates to the Boltzmann distribution, which we will go through soon. In most collisions, the molecules collide, but then bounce off each other and remain chemically unchanged. This is why reactions take time to take place, because as soon as you put the reactants together, they don't all collide in the correct way. So it will take time for them to collide in the correct way. And these factors, which we saw before, can increase the rate at which they collide effectively. This explains why some collisions are effective and others are ineffective. The particles need to collide with the correct orientation and have sufficient energy to overcome the activation energy barrier of the reaction. So here you can see two blue atoms must collide for the reaction to occur. So it needs to be in this orientation. And they'll also need to have enough energy to overcome they'll need to have more energy than the stated activation. So the rate of reaction can also be defined as how fast the reactants turn into products. And you can find out the rate of reactions a lot of different ways. But here there are two ways to determine the rate of chemical reaction. This is one of them. Here, by the way, it just says the rate at which the reactants are used up, or the rate at which the products of the reaction are made, which, if you remember, are, let's see how quickly we can go back there, how fast the reactant is being used up, or how fast a product is being formed. So we said that earlier. Okay. Now, 3 techniques you can use to do this, which I'm sure you'll be familiar with, and we've used it in some of the content which we went through earlier today. So you can measure the rate at which the mass of a reaction mixture changes if the reaction gives off a gas. So that was with the CO2, as we said earlier. Excuse me. As the reaction takes place, the mass of the reaction mixture decreases, and this can be measured at regular time intervals. As we can see here, we have time, and then we can plot it with the data that you collect. And then you draw the line of best fit. Well, that's just the reaction that has taken place. Secondly, it can be measured in the increasing volume of gas that has been given off. You must have used a gas syringe. I'm not too sure if you still do that, but the reaction will occur here, and then gas will be formed. And this gas syringe, it starts off here, okay, and that's 0. And then as gas is given off, it pushes this syringe up, and then you can measure how much gas has been produced. But this is obviously can only be used if the reaction produces a gas, and then it collects the gas and gives you the volume. And again, it's at time intervals. intervals so that you can form the curve. Again, it can be used to measure, it can be measured by looking at the decreasing light passing through a solution. And this can only occur when the reaction produces a precipitate. And this precipitate will, as you can see here, it will make the solution cloudy. And if you see, so you usually draw an X on a piece of paper and see how quickly that X disappears. And this can be used to measure the rate at which the precipitate appears. So what is not required for an effective collision? This is a, I've tried to be fun here. Obviously it's D, because you don't really require pure skill, really. Carry on. I don't know why that just turned red. That shouldn't have turned red. So here you can calculate the rate of the reaction between 5 and 15 seconds. Okay. And then you can see the volume of gas at 5 and the volume of gas at 15. And then here you can see it's 18 minus 12, which gives you 6 centimeters cubed of gas produced in that time period. And then you can see the change in time, which is, that's 10 seconds. Or have they given me 5 seconds? Anyway, and then you should do 6 divided by 10. That should not be 1.2. That should be 6 divided by 10. I don't know why that's not correct. And then that would be your answer. Now the rate of the reaction is not 1.2. I don't know why that's incorrect. It would be 0.6 centimeters cubed. Now the students added a dilute hydrochloric acid to some, I can't see that, that says magnesium strips, magnesium carbonate. The students collected the gas and measured the volume at regular intervals until the reaction was complete. They then plotted a graph of their results. Now this is using the collision theory, explain the changes in the rate of reaction as it proceeds. So this is 3 marks, so you should have 3 essential points. Now the mark scheme says, as the reaction proceeds, the concentration decreases and the rate of collision decreases. The reaction stops when all of one reagent is used up. So when all of one reagent is used up, there's nothing left to react. Okay. And these are the 3 points which are essential to answering why there's a change in the rate of reaction as it proceeds. Okay, so as the reaction proceeds, it says it collects gas. So gas is being produced. And as gas is produced, the concentration decreases and decreases until all of one reagent is used up. Now, catalysts, let me have a look at where we are in terms of where we need to be. Okay, we've got a bit to go. Would you like to have a break or would you like to carry on? We can have a 5-minute break until 45. Carry on. All right, cool. So catalysts. A catalyst is a substance that changes the rate of a chemical reaction without undergoing any permanent change itself. That is the standard definition, and that should be your only definition of a catalyst. Okay. And then this is just a little diagram. The catalyst is not used up in the chemical reaction. That's why it says it does not go under permanent change. It may react with a reactant to form an intermediate, or it may provide surface on which the reaction can take place so that they're in the correct orientation. It forces them to be in the correct orientation. At the end of the reaction, the catalyst is regenerated. Again, this is relating to without undergoing any permanent change itself. A catalyst increases the rate of chemical reaction by providing an alternative reaction pathway of lower activation energy. We already know that. And we've been through this earlier, didn't we? And this is one activation energy. This is another activation energy. And that is with a catalyst. And this increases again because it provides an alternate path of lower activation energy. This is the lower activation energy. And again, so that's for endothermic and exothermic, but just make sure that your catalyst EC is always smaller than your normal one, because that makes sense according to this fact. We have different types of catalysts. We have homogeneous catalysts, which means that it's in the same physical state as the reactants. And these catalysts react with the reactants to form an intermediate. This intermediate then breaks down to give the product and then regenerates the catalyst. So for here, we can see that C2H5OH plus C3H3COOH. There's an equilibrium reaction here. CH3COO, I don't need to read that out. Anyway, you can see here, this is the intermediary. Okay. No, that's the catalyst, sorry. So you're making esters here. That's the catalyst, just to reinstate. You're making esters with sulfuric acid as a catalyst. And it's also a liquid, right? Which you can see here. And so it's the same state as everything else. Again, the same state as everything else. And then this is ozone depletion. I'm not sure what board you're doing, but I do remember that when I was doing this, I needed to memorize this equation. But again, check on your syllabus and see whether you need to do that. Now, you can also have heterogeneous catalysts. And as you could guess, it means that they have a different physical state from the reactants. These are usually solids in contact with the Gassian reactants or reactants in solution. Reactant molecules are absorbed and then weakly bonded on the surface of the catalyst where the reaction takes place. And here we have certain processes of making ammonia, which is the Haber process, with an ion catalyst, and again, the equation. Once again, I remember I had to memorize this one and this one. Actually, I had to memorize all of them. So again, double check your syllabus. This is just memorizing. But again, this is these are just examples of heterogeneous catalysts where the form that they're in is different from the ones in the actual equation. After the reaction, the product molecules leave the surface of the catalyst by desorption, and then this leaves the catalyst as it was at the beginning. Now, catalysis, in terms of sustainability and economics importance, it's essential in industry. It's estimated that 90% of all chemical materials are produced using a catalyst, and they increase the rate of many industrial chemicals by lowering the activation energy. This reduces the temperature needed and the energy requirements, which again reduces costs. Well, yeah, there we go. Less electricity or fossil fuels is used. Making products faster and using less energy is benefits on both halves. So that can cut costs and increase profitability because you're making products faster. So this economic advantage of using a catalyst outweighs any costs associated with actually developing it. And this focuses on sustainability in the industry to operate processes with high atom economies. High atom economies are good and fewer pollutants, which is obviously good as well. So what is meant by a catalyst? This is an exam question, so it should be something you can memorize. And 2 marks means there are 2 significant points which you should make. The first one is it's a substance that alters or increases the rate of reaction or lowers the activation energy. Could be, you could say either or. And again, the important bit remains unchanged after the reaction or is used up. Here it says, suggest 2 reasons why catalysts are used in industrial processes. This is just reiterating, writing down what I've just been through, the economical the economical advantages. So one would be to save energy or money. This allows, you'll need to give a reason here to get the mark. This allows the process to run at a lower temperature by lowering the activation energy. Another reason is so that it goes faster to save time, which allows the process to run continuously, and that increases profits. The profit bit isn't required, obviously, here, but going faster saves time. You have your reason here. Now we move on to Boltzmann distribution. Yeah. Now the key features are that no molecules have 0 energy. So the curve looks like it starts at the origin, but it doesn't, okay? Does not start at the origin. The area under the curve is equal to the total number of molecules that are taking place, that are in the reaction. And there's no maximum energy for a molecule, so the curve does not ever meet the x-axis. And the curve would have to reach infinity energy to meet the x-axis. That's just an extension of this statement. So this is an example of the Boltzmann distribution. Here we have number of molecules with a given energy. So these are just the energy levels of molecules. Okay, so here, again, we can see if we look closely, it does not start at 0 and it does not meet the x-axis. So this is, look carefully, this is not energy. This is not level of energy. There's the energy requirement. So that's the activation energy. This is the number of molecules. So most of your molecules have this level of energy. And that, as you can see, most of them do not have the required energy to overcome the activation. So this is just repeating what I've said. The graph is marked with a line that represents the activation energy. And from the shaded area, only a small proportion of the molecules have more energy that's enough to react. Now, looking at, sorry, let me get to the right page. Looking at the Boltzmann distribution and then the effect of temperature, at a higher temperature, more molecules would have greater energy, or more molecules would have them equal to the activation energy. Therefore, a greater proportion of collisions will lead to a reaction, and this increases the rate of reaction. I'll just go through that again. So at a higher temperature, more molecules have energy greater than or equal to the activation energy. And therefore, a greater proportion of the collisions will be effective, that lead to a reaction, and this increases the rate of the reaction. Collisions will also be more frequent as the molecules are moving faster, but the increased energy of the molecules is much more important than the frequency of collisions, because as you can see with the Boltzmann distribution, energy is the main thing that's important. This shows the effective temperature. So at a higher temperature, T2, the peak is lower and shifted to the right. And this is because a greater proportion, as it says here, of molecules can overcome the activation energy, since there are more molecules with a higher energy level. Now remember, this is not this here, this is energy. A lot of people get confused. This is energy, and this is number of molecules. So as soon as you understand that, Boltzmann distribution should be very easy to understand. Now, an exam question, the diagram below shows the energy distribution of molecules at a particular temperature. EA represents the activation energy of the reaction. On the diagram, draw a second curve to represent the energy distribution of the same number of molecules at a higher temperature. Literally just done this, the curve is displaced to the right, the maximum is lower. Those are the two things that need to happen. So it should look a bit like this. So as you can see here, the proportion of molecules over the activation energy of the original curve is less. Nope, sorry. So this is the original, and then with a higher temperature, these are all included as well. Now with a catalyst, you can also see this, because as we know, with a catalyst, there is a lower activation energy. So with temperature, as we can see here, the energy increases, okay? Because the collisions are more frequent and the energy of the molecules are important, right? So this is what's changing with temperature, number of molecules with a given energy, because more molecules have higher energy. With a catalyst, this curve does not change. It's the activation energy which changes. So because the activation energy with a catalyst is lower because of the definition, then you draw another one here. And again, you can see a greater proportion of molecules have energy which can supersede the activation energy required to proceed to the reaction. So a catalyst provides an alternative route with a low activation energy, and then compared to EA, a greater proportion of molecules now have energy equal to or greater than the lower activation energy. On collision, more molecules will react to form products because there are more molecules over the energy to do so, like available. And the result is an increase in the rate of reaction. Now, this is an exam question. Cars are fitted with catalytic converters in order to reduce pollution. Jesus. Potential pollutant gases include carbon monoxide, nitrogen monoxide, and unburnt hydrocarbons. The first two compounds are removed by bypassing the hot gases over a platinum catalyst. For the first part of this question, as you can see, it has nothing to do with this. Okay, it's just define the term activation energy. This, again, is just something you're going to have to remember. It's the energy the molecules must have to react or start the equation. Now is where you need to read the question carefully. It says, draw a distribution of the molecular energies of gas molecules at two different temperatures. Okay, so we're looking at temperatures. T1, normal temperature. T2, higher temperature. Label the curves T1 and T2. Mark the energy corresponding to the activation. So we know that with temperature, we've just gone through this. Say it doesn't matter where the activation energy is. This is just a representative distribution. So say we put the activation energy here. That's EA. Okay. And then just draw any curve for T1. Okay, so it's like that. Now, the important bit is that you need to now make another curve with a higher temperature. Just use the same concept we used before. The peak must be lower and there are more higher area under the curve. Remember, the area under the curve is proportional to the number of molecules. Okay. Here's the mark scheme. So T1 skewed, no intercept of y-axis. This is important, okay? It must not touch 0. So it has to start there, just to the right. And it cannot touch the x-axis as well. T2, the peak is lower, which we did, and to the right of T1, and it's not consequential. So that doesn't matter. So the shape of the curve doesn't matter. As long as there's a peak, it's skewed, and you've got the right pattern for increased in temperature. Now, using the diagram, you need to explain why the rate of reaction will change as temperature increases. This is another reiteration of the content we've just done, just in an exam technique scenario. So you need to comment on, with an increased temperature, there is a greater area under the graph, which leads to more successful collisions. And then it says here could be shown on the graph. So if here we've got one, whoops, that was awful. 1 and T2. And that's activation energy. Should label all of them. So you can just say this is the greater proportion of molecules that you'll need for more successful collisions. And then this increases rate of reaction. And now the reaction between carbon monoxide and nitrogen monoxide requires a platinum catalyst with a large surface area. Explain the effect of a catalyst on the rate of this reaction and why the surface area needs to be large. All right, and then this bit here is just knowledge of chemistry, basic knowledge of chemistry. But again, in an exam scenario, there's specific things that you might need to mention that you might not know of. Explaining the effect of the catalyst, we've just been over that. So we'll look at the points that they give. So the catalyst, first thing is to define it. It gives an alternative route with a lower activation energy. And then know that the why surface area is important is because the reaction only takes place at the surface of the catalyst. And then explain if this has a large surface area, this will increase the chances of collision with gas molecules since there are more active sites. The higher the surface area of a catalyst, the more active sites there are, the more molecules attached to it, the increased chance of collision. So if you understand the concept of collisions and you understand the concept of activation energy and increased rate of reaction, then you'll be able to formulate these marks, no problem. So if you think about it, everything we've been building on today relates to one another. If you understand the beginning, you understand each section that we've been through, then each question will get easier. All of the rules, the definitions, just go through them, and that will help. Now, using your completed diagram, explain how an increase in temperature causes the rate of reaction to increase. This is not related to the one before. This is just a different question, but instead of drawing it now, you're explaining it. Here we see that the area under the curve exceeding the activation energy is increasing. Okay, that's that point there. So a lot of people will write this and only get 1 mark. The first thing you need to do is define that the area under the curve exceeding the activation energy is equal to the number of molecules that can react. So you remember at the beginning of the Boltzmann distribution, we said that the area under the curve equals the number of molecules. And so when you have your activation energy, that cuts the curve at a certain point, and the area at that point is equal to the number of molecules that can react because they are equal to or higher than the activation energy. Then you can use the increase in temperature, and at a higher temperature, the area under the curve is greater than that when we have activation energy, and is greater, so more molecules can react. Now, these are this is just a question for before. It says some mean bond enthalpies are given below. Use these data to calculate the enthalpy change for the following gas phase reaction between hydrazine and hydrogen peroxide. So yeah, this is just a calculation, as we said before. One of the most important things here, if you remember, is knowing that there's 2 here and 4 here, which means that when you calculate and you add the sum of these, you'll need to times it by 4, and the sum of these times it by 2, and then use that in the equation. Okay. Also, you'll need to use, this is mean bond enthalpy of formation. Okay, so these are formations. But sometimes they'll ask you to do the formation diagram, and that's somewhere that you need to really look at when you read the question. In this case, it's not. But I just remember that used to be something that a lot of people got caught out on. So read the question carefully, underline the relevant bits of information, and then look at everything they've given you and take out the bits that you need. So the answer to this, the enthalpy change is the sum of the bonds broken minus the sum of the bonds formed, or you can do the cycle, okay? It depends whichever one you find easiest, and you should come to minus 789. It seems like we have finished just on time. If you have any questions, please let me know now. If not, then thank you for coming. And if you've recorded this, then we've recorded this, so obviously you can go back and watch it again. Yeah, thank you. If you have any questions, let me know now. And then in about a minute or if you don't have any questions, then I'll stop the lesson. All right, brilliant. Thank you. Cheers. I hope that was helpful. Yeah, well, that's all. I hope it was helpful. Thank you. Cheers. I believe you may go, I think, probably.